welcome to the ARPA-E Summit Fast Pitch. Today, we'd like to talk about accessing energy in new ways so that we can minimize environmental impacts. We call it leave it in the ground, but use it too. I'd like to start by thanking Doctors Elena Chung and Sade Ruffin, tech seeders who work with me at ARPA-E, for their help with this presentation. Let's start by looking at how our intrepid ancestors accessed energy, starting back in the Stone Age. It was a pretty simple process, 3 steps: gather, transport, and burn. Today, 50,000 years later, we pretty much use the same 3 steps: gather, transport, and burn, only now we do it at a massive scale. 15 billion tons a year of energy-dense fuel is mined, moved around the world, and burned in sophisticated machines that enhance energy efficiency. There's a lot of environmental impacts, and ironically, our solution for the environmental impacts is to bury 50 billion tons of CO2, ash, and tailings. So maybe it's time to rethink how we access energy, come up with a new set of rules to guide our use of energy. And so we'd like to suggest perhaps 3 new rules to think about. Let's minimize extraction. Let's only move what we have to. Let's keep it simple. Instead of using sophisticated hardware that maximizes efficiency, let's think about simple devices such as electrochemical cells, which have few or no moving parts. And finally, let's look at processes that are inherently clean so that there's no mess and nothing to bury. Sounds ambitious, but let's look at some examples. Here's one: getting more energy out of existing oil and gas wells. Oil wells start with fluids underground, oil, gas, and water, that are heated because of underground temperature gradients, and they flow up to the surface where they're separated and also cooled. The water is usually re-injected either to dispose of it or to maintain the downhole pressure. This cool water going back down into the downhole environment where it's hot creates an opportunity to generate electricity. 2 researchers at the University of Oklahoma show us how. Let's start by modifying our well that we saw in the previous diagram by putting a pipe in a pipe down into the hole. Cold water from the surface flows in the inner pipe and then flows back up to the surface in a middle pipe. On the outside of this middle pipe, we install a ring of semiconductors. Those semiconductors can use the temperature gradient to generate electricity. The voltage is small, but if we put them in series, we can increase the voltage so it's easier to move that electricity back up to the surface. It's a simple device. There's no moving parts. There's no new fluids to dispose of, and we've minimized digging. So we've achieved our goals. Here's another example, this time using abandoned mines and wells. The thing to remember with abandoned mines and wells is that there's still a lot of hydrocarbon resources available. Typically, only half the hydrocarbons get extracted. So let's think about putting a microbial fuel cell down inside an old abandoned mine, for example. Over on the anode, we have electrolysis. These are bacteria that can eat some of those organic molecules from the unrecovered coal, oil, or gas and generate electricity. On the cathode side, we can inject air or oxygen into the mine, and down in that section, we'll generate water. And so we have a fairly simple system here that makes electricity using existing underground infrastructure, and there's nothing to clean up. It's inherently clean. We can use the same kind of system to generate hydrogen. If instead of producing electricity, we inject electricity, and we don't inject air or water or air or oxygen at the cathode, we will generate hydrogen. The same as an electrolytic cell, electrolyzer cell that makes hydrogen from electricity, only now the biology is doing most of the work, so we need much less electricity to split the water into hydrogen. Here's another example, also reusing underground infrastructure. This is a project that's being studied over in Germany, and they're looking to use underground salt caverns, old salt mines, to store electricity. It's a pretty simple process. You start with a flow battery, and the flow battery uses 2 fluids, a catholyte and an analyte, which are pumped up to the surface when the sun is shining and the wind is blowing to charge up these solutions, and then they're stored underground. When the wind and the sun are not available, these fluids are pumped back up to the flow battery and generate electricity. These solutions are recycled indefinitely, so there's no waste, and we're reusing underground infrastructure. So we can essentially create very large batteries with minimal environmental impact. And here's a final example, again using an electrochemical cell, this time that generates electricity based on salt gradients. When you have fresh water, say a river contacting the ocean, you basically have two streams with very different salt concentrations. If instead of just allowing these to mix in the ocean, we first put them through an electrochemical cell, putting the low dilute salt water on one side and the high concentration salt water on the other side, we can generate electricity. And with this process, we basically get free electricity because we're not needing to move any new streams. It's inherently clean, and we have a very simple device. So what I'm hoping to have convinced you is that there's a lot of opportunities to rethink how we access energy. We need to come up with some new rules, such as try and minimize the movement of mass. Let's keep it simple and let's keep it clean. Now, there's a lot of challenges with this new approach. We have to recognize that our existing energy infrastructure was developed over thousands of years based on a different set of rules. And so we have to rethink every step with this new process. We have to look at energy aggregation. For example, many of the devices that I've talked about generate low voltages. And so we need to aggregate the energy to make sure that it meets the requirements of our modern society. We're going to have to figure out how to efficiently move electricity from underground to the surface. And we're going to need entirely new communities comprised of scientific, engineering, and business people who can develop new approaches to take advantage of these new technologies. Nature has given us a lot of clues as to how we can minimize our environmental impact while still enjoying the benefits of energy. And I suggest it's incumbent upon us to try and develop these tools. So with that, I'd like to thank you for your attention. I look forward to your questions. And I'd like to introduce Dr. Marina Sofos, who's going to talk to us about how buildings can help minimize CO2 footprint in the environment. Thanks for your attention.
Thanks, Jack. Hello, everyone. My name is Marina Sofos, and as both Jack and Scott mentioned, I'd like to talk to you today about the opportunity to transform our buildings into carbon sinks. But first, let's start at the beginning of the story, roughly 10,000 years ago, with the first agricultural revolution. At that time, humans transitioned from hunting and gathering, where only temporary shelter from the elements was required, to the need for more permanent settlement near one's source of food production and storage. And so this transition also gave rise to the first buildings. Natural materials were used back then, but as Jack noted, the way we make and use energy evolved with each subsequent agricultural and industrial revolution. And with that, the production of materials, the ways in which we design and construct our buildings, and the associated emissions also grew, such that today, those emissions derived from the raw material extraction, processing, transportation to site for installation, and the actual construction adds up to 11% of total global annual emissions. A large chunk of this is attributed to the energy-intensive nature of making the most common materials used, including aluminum, concrete, steel, refrigerants, and spray foams used for insulation. On the other hand, when it comes to the emissions associated with operating our buildings, more than 40 years of innovation, along with more stringent codes and appliance standards that have driven adoption, have resulted in projected declines each year, with a forecasted 29% drop in 2030 compared to actual 2005 levels. This makes it even more important to address embodied emissions. To put it into context, a building constructed today, like the Unisphere outside Washington, D.C., that is also the world's largest commercial building that is net zero energy in its usage, will take on average 35 years in its operation for the upfront or embodied emissions to be offset by the accumulated operational emissions according to a paper last year by Rock et al., showing the temporal occurrence of emissions across the building life cycle. Now, this is longer than the 10 to 20-year timeline for the average building today because of the additional emissions associated with making materials for more efficient operations. Now, if we also assume lower emissions from a cleaner grid, the timeline increases to 50 years because the associated reduction means that embodied emissions comprise an even larger percentage of the overall total. So there's a real urgency to act here. Even though accumulated operational emissions exceed embodied over a building's lifetime, the embodied emissions are locked in at the start of operations, as evidenced by the spikes on this graph, which means that the timeline for upcoming new construction coincides with the window in which overall emissions need to be reduced by 2050 so that temperatures don't rise above 1.5 degrees C. As Scott noted, negative emission technologies are imperative to cooling the planet. The 50 to 100 year average lifetime of buildings, along with the sheer amount we manufacture each year, nearly 66 billion square feet, makes them particularly attractive carbon sink candidates. But to do so, not only do we have to think in terms of reducing emissions, we also need to draw down and retain carbon so that the net carbon dioxide equivalence, or the difference between the mean emissions estimate to manufacture the material and the mean storage estimate, is negative. So let's take a closer look at the other factors in addition to the overall carbon storage that needs to be considered to make an impact. Now, all approaches hinge on a full life cycle analysis, but we should bear in mind that at this stage, not all elements are well qualified for full evaluation. But to begin, we have to consider the land and water use implications for a given feedstock, along with the distance between source, production, and site construction. The source of carbon will have implications on the final quantification. And finally, as I'll elaborate in a couple more slides, the mechanism of carbon storage can be temporary or longer term in nature. The efficiency of building operations can't be sacrificed as a result of utilizing a net carbon storing material. And finally, the overall performance lifetime, including the emissions associated with end of life and retention of carbon, play a role. A variety of feedstocks are being pursued for these purposes, including forestry and purpose-grown products, agricultural residues, and direct use of carbon dioxide to create carbon-based materials. Depending on the feedstock, there can be a wide variability in land use requirements, however, as shown in a recent publication by Will Schrubar for common biogenic feedstocks on an annual ton of carbon by hectare basis. Now, in terms of storage, permanent sequestration can be provided by carbonate mineralization by locking in atmospheric carbon into a molecular structure. For these solutions, advances that will meaningfully increase the amount sequestered compared to the amount emitted in manufacturing must be further developed. On the other hand, biogenic pathways, which rely on photosynthesis, generally have lower upfront emissions, but carbon may be released into the atmosphere again over time. So ultimately, both of these strategies have limitations that require further exploration to address, but both will play a role in meeting our climate goals. Now, taking a further look at the storage timescales, an analysis conducted by Lawrence Livermore, which evaluated carbon release activities over 10,000 years, also shows wide uncertainties that need to be accounted for depending on the type of storage, in addition to the timelines for retention strategies. Further development of carbon negative manufacturing can also provide valuable data to better forecast and validate these numbers. So I'd like to leave you to consider ideas for how we can extend the lifetime of carbon storing building materials, including what are the ways in which near-term biogenic approaches beneficial to meeting near-term climate targets can later be converted to more permanent storage within an acceptable timeline. And also, how can carbon storing materials be reused in buildings designed for disassembly to avoid landfilling. With that, I think it's fitting to end with a quotation from Winston Churchill. And so I'd like to thank you for your time and look forward to further discussion with you on how we can shape our buildings to be carbon sinks. Now I'd like to hand it off to my colleague, Program Director Scott Litzelman, who will be talking to us about the future of direct air capture technologies. Thank you.
To continue this topic of removing CO2 from the air, I'm going to talk about direct air capture of CO2, or DAC, and the implications it could have on our energy system if we do it at scale. When we think about technologies to decarbonize our grid, there's a variety of technologies like renewables, or energy storage, or nuclear power, or transmission capacity, fossil fuels with CCS, and others. And there's no one right way to decarbonize. It's going to look different in different parts of the world based on regional grids, based on policies and scenarios. It's not going to be one way of doing it. And sometimes people get into an argument about what it might look like. And I kind of think it as a game of chess. So the ultimate goal is to decarbonize our energy system. And there are different pieces with different roles, and different games or different scenarios could play out differently. But basically, we know what the pieces are, we know what the roles are. Well, the point I want to make is there's a piece of the decarbonization chessboard that we're not talking about enough, and that's DAC. Now, you might say, Scott, that's ridiculous. DAC is getting a lot of attention right now. And that's true. In the last few months, there have been several announcements of corporate procurements of DAC, which is important because they're buying DAC when it's relatively expensive as a means to scale up the technology and bring the cost down. So there's actually a lot happening in this space right now. But when I say we're not talking about DAC enough, what I mean is we're not talking about the interactions or the interplay between DAC and the other pieces of our energy system or the pieces of the decarbonization chessboard. And I'll tell you what I mean. Let's start with a number, 600 megatons of annual CO2 removal via DAC in the US by 2050. That's an estimate I made from a number of citations from the literature at the bottom. And there are two things I want to say about this number. First, there's a large uncertainty behind this number. In some of those references below, their models in 2050 were deploying 0 DAC. Now, there were other scenarios where the models were deploying more than 1 gigaton of DAC per year. So there's a lot of ranges in this number. And the other point I want to make about it is that this assumes that other forms of CO2 removal from air are happening. So bio approaches like biomass approaches or soil carbon or afforestation, reforestation, this number assumes that we are already doing this thing. So this is in addition to, not in lieu of those other things. So it tells you how much CO2 removal we need in the future. Now, direct air capture is a very energy intensive process. It takes a lot of low carbon heat and low carbon electricity to operate. And if we took today's technology and said, okay, with the current technology, if we did 600 megatons per year via DAC, it would require 970 terawatt hours of heat and about 250 terawatt hours of electricity. Now, to put those numbers in context, just under 1,000 terawatt hours of heat is the output of 39 1 gigawatt nuclear plants, and 250 terawatt hours of electricity is the annual consumption of the state of California. So to do these technologies at this scale, we'd be adding 39 nuclear plants worth of heat and 1 large state's worth of electricity to our energy system. So when I say we need to talk more about the energy implications of DAC at scale, this is what I mean. Now, fortunately, some researchers are already starting to consider this. On the left is a plot from the lab of Jennifer Wilcox, who's now the Principal Deputy Assistant Secretary at the Office of Fossil Energy. And what they looked at were existing sources of low carbon heat. So existing nuclear plants or geothermal resources. And they also looked at potential CO2 storage sites. And they're trying to find ways of reducing the cost of DAC by co-locating and optimizing the heat input and the ultimate repository for the CO2. Now, conversely, Princeton University, when they released their Net Zero America study, they assumed electrified DAC, and they actually considered it to be a flexible load. So this plot on the right, the gray area are essentially inflexible loads, and then there are different scenarios. They have differing amount of flexible loads, one of which is DAC, so the ability to turn it down or off if renewables or some situation required it. And this is really good. These two studies, it's great that they're starting to think about these technologies and what the integration looks like, and I think we need more of this. And specifically, I think we need to consider technology development and system modeling hand in hand. because there's some DAC technologies that are being commercialized now, but it's still very early days, and there's still room to consider advanced technologies and integration from the very beginning. And I kind of break this down in two ways. One is technology that has a similar ratio of heat to electricity as current DAC processes. So mostly heat, some electricity. Conversely, you could also consider fully electrified DAC, which is something that ARPA-E and others are starting to work on. Now, when we think about mostly heat and electricity similar to today, I mentioned integration of existing nuclear plants from the Wilcox lab in the last slide. While in the ARPA-E Flex program, one of the things we're also considering is integration between fossil fuel power plants with point source CCS systems and DAC systems, because we see those fossil fuel plants with CCS as important from a firm capacity point of view, but they might not have that high capacity factor because the price of electricity is going to be higher. Well, there could be times where those plants are turned down where they'd have low carbon heat and electricity available for the DAC system, so it increases the utilization of that power plant, and it's providing valuable services instead of electricity by removing CO2 from the air. So that's something that we're looking at with several of our Flex projects. Now on the right, when it comes to electrified DAC, there could be electrochemical approaches, there could be electric-based heating approaches, and one of the things that comes to mind is transmission capacity. Now early on I showed some transmission lines, and as we dispatch more renewable power, having more transmission capacity is really valuable. But now if we say, well, electricity demand is going to increase even more because all of this electrified DAC that we have, well, it means we need that much more transmission capacity. And it's one thing to say, oh, we need lots of transmission capacity, but it's a different thing in the US to build it because it's very costly and it takes a long time to build those transmission lines. So it's something that we need to think about. Now, the flip side and the positive side is all that electrified DAC could be a demand response asset. So in times of extreme weather events or severe stress in the grid, the ability to turn down or turn off those DAC systems provides a lot of flexibility to grid operators. And so really there are two benefits. The first is just the benefit of removing CO2 from the air, but the ability to provide extra flexibility to the system is going to be really valuable in the future. So hopefully I've convinced you of the importance of thinking about what energy integration of DAC looks like if we do it at scale. I've been thinking about this, but I'd love to get your thoughts. So in the Q&A after the session or other points of the ARPA-E Summit or afterwards, I'd love to hear what you think about this, and I look forward to discussing with you. So with that, thank you very much for paying attention to this, and I hope to enjoy talking to you soon. So now I'd like to introduce Dr. Ian Robinson to finish off our session. Ian's going to be talking about what ways that we might be able to utilize all the CO2 that we'll be capturing in the air in more clever ways. So Ian, please take it away.
Hello, everybody. My name is Ian Robinson, and I'm a fellow here at ARPA-E looking at different carbon capture and utilization technologies. And today I'm going to be talking to you about carbon capture, and we're going to try and fill in the blank here. So let's walk through a typical carbon capture system. Now, we want to take carbon from a point source like a power plant or industrial process, or a dilute source like the air or the ocean, and capture it into a metastable state. And this is going to be, CO2 in some sort of capture media like a solid or a sorbent or solvent. So once we've done that, we still have some additional steps. Once we have our CO2 in the capture media, we have to then input a significant amount of energy to get back to some sort of, pure CO2 in a pure CO2 stream. And now we have to decide what to do with it. And here, there's going to be a couple of different routes. So there's going to be either a need for carbon in some sort of a hydrocarbon that people will probably try and do CO2 utilization for, or they're going to try and sequester the carbon because, as you've seen, we need to get to net negative emissions by the end of the century to meet our climate goals. So if your decision is to utilize the carbon for, making hydrocarbons, this might not be the best route for you. We need to probably reimagine the carbon capture system with a new idea, where instead of taking the carbon in the capture media to CO2, we take it to a useful molecule in this new idea where we regenerate the capture media to get to something like carbon monoxide, methanol, or formic acid that could be used in some sort of upgrading route like a Fischer-Tropsch or a methanol to jet fuel plant, where that can be used to decarbonize some sort of hard to decarbonize industry. And the key for this is going to be this regeneration step of the capture media and synthesizing a useful product with very high energy efficiency. So let's walk through kind of a basic overview of carbon capture. And I'm going to use, direct air capture as an example. They typically use some sort of hydroxide and they capture CO2 from the air. And then they go down to some sort of high carbonate or bicarbonate. And doing this to utilize CO2, people have typically thought, okay, we'll regenerate back to CO2. This is going to be a very capital intensive step. And then we're going to utilize CO2. This is also going to be a very capital intensive step to get to some sort of useful molecule that we can see here. Well, instead of doing two very capital intensive steps, we need to rethink this and do, direct air capture media directly to a useful molecule with one set of capital, instead of repurifying back to CO2 and compressing it and doing all the things that you need to do to utilize CO2 by itself. Instead, let's just go directly to the useful molecule. Now, here's an example. This is one of the currently being commercialized direct air capture companies. This is their front end process. This is Carbon Engineering's process. And what they do is they take CO2 in some sort of front end with a capture unit and hydroxides, and they take the hydroxide carbonate, and then they cycle that with calcium carbonate and calcium hydroxide to get to calcium carbonate. And then they cycle that into a calciner, and then they do an oxifier calcination step to get to a pure CO2 stream. And then they compress that and they figure out how to utilize that if the end goal is CO2 utilization. This is very capital intensive. The pellet reactor, calciner, and compressor are all very energy and capital intensive. So instead of doing all of this just to get back to CO2, we can rethink, okay, well, why don't we just do some sort of regeneration step that allows us to use our capture media directly. So here we can think about using something like bicarbonate electrolysis to get back to, formic acid, methanol, or ethylene, something like that, instead of doing all of those intermediate steps just to get the CO2 and re-electrolyze it. This is going to be much more capital efficient than any of the other methods. So let's go ahead and look at, now we're going to do some sort of reactive carbon capture that we described earlier, and we have to figure out what we want to make. Well, there's a lot of talk in CO2 electrolysis reviews that you can go ahead and make formic acid or carbon monoxide at profit, but let's look at the actual production capacities per year. Well, if it's only, on the megaton or the single digit megaton scales, that's not exactly impactful. We need to go after, gigatons of carbon dioxide, per year. And to do that, we need to use molecules that can be fed into a downstream process to unlock things like diesel or jet fuel. So to do that, we have to regenerate very efficiently to bring that cost down below our jet fuel or diesel curves, so we can use that as a feedstock. Now, we figured out what we want to make with CO2 from this reactive capture standpoint, and we have to figure out, okay, how we're going to upgrade it. Well, we have established commercial upgrading methods for these feedstock molecules that get us to very desirable products like jet fuel, diesel, gasoline, or polymers. And a low end estimate, this is going to be about 2 gigatons per carbon per year, which is a significant chunk. So this is kind of the general idea, is that we're going to make this drop-in replacement to upgrade and unlock these carbon neutral fuels. Now, this is going to fit into our portfolio approach for decarbonization, where we need to go after things like aviation, shipping, iron and steel, cement. Any one of these is going to be hard to electrify and hard to decarbonize. And, there's some different approaches that are going to be, pursued. The first one is just do business as usual, and the company is going to buy a direct air capture offset to offset the carbon emissions. And this is going to be pretty expensive. The next route is to electrify the hard to decarbonize sector. This is something we're actively pursuing under Reach and Ascend, and it's a hard task still. And I hope that I've shown you today, maybe we could use reactive carbon capture to synthesize a drop-in neutral fuel. So where I'm looking for your feedback is, Well, I want to see some new technical ideas that could fit into a reactive carbon capture system and allow us to unlock these hard to decarbonize industries and produce carbon neutral fuels for any one of these industries. My email's on the screen if you want to further contact me or just talk to me here at the summit. And now we can open it up to questions.
Thank you, everyone, for the presentations, and thank you for sending your questions. I see some over here. I know we've got more. Please continue sending in. We want to get to as many as we possibly can. And I'm going to start. And I should also mention, too, there's a little caret to the left that you can use to upvote. So if you see a question that you think is really great, click on it and it kind of gets booted up in the list. And using that upvote, Marina, I'm going to throw this one to you first. Someone asked you what considerations are necessary to deliver negative emissions in addition to avoided emissions. And Marina, you're on mute.
Sorry about that, everyone. It's been 15 months. We should be used to the double mute by now. Yeah, thanks, Scott. So that's the full life cycle is really imperative to consider if we want to get to negative emissions, or as we put it, as I put in the fast pitch, carbon negative building materials. So in other words, it's not just a matter of reducing the emissions, but taking into account the sourcing of where the initial CO2 is coming from, and reducing, and not just reducing, but storing an equivalent amount that in net total it overcomes any emissions from start to finish. Okay,
great, thank you. One question that came up, has a very large number next to it, is about XPrize. And someone wrote that XPrize has a new $100 million prize for CDR, which is carbon dioxide removal demos. How does this relate to RB's interests or other target areas? And in general, I think the objectives are very much the same. So if you go to the XPrize site and you look at the carbon removal prize, it is about just removing CO2 from the air and storing it in a stable way. They're not particularly prescriptive of how to do that. They say direct air capture or oceans or mineralization. I think there's a lot of routes. From what I understand, it's happening over the next 4 years, and you have to show technology that can, I think it's maybe 1,000 tons of CO2 per year, but with the potential to scale much larger than eventually to scale to gigatons. I encourage you to check it out. There are probably technologies that may be a little bit more farther along than some of our projects, which tend to be a bit earlier stage. But in general, I think it shows that, it's certainly not just ARPA-E. I mean, other parts of DOE, like the Office of Fossil Energy, and the BIO is doing this. There's just a lot of work happening in this space right now. And so I encourage you to check out XPrize because, again, $100 million prize pool, it's pretty attractive. Okay, let's go to Jack. There's a question for you. What reservoir features are most appealing for subsurface microbial fuel cells?
And it's a good question. The biology for microbial fuel cells has been commercialized for wastewater treatment plants. And I think what you'd probably need to do is look at specific environments. It's certainly known that there's quite a host of methanogens and other biology. It's documented in oil and gas wells, and also to a lesser extent in coal mines. But even within those categories, there's quite a spectrum of downhole temperatures, pH, salinity, et cetera. So I think you'd really need to start with a characterization of what you think the suitable electrolysis would be, and then match those against the downhole characterizations in terms of the local environment. Again, temperature, pH, other considerations.
Okay, great, thanks, Jack. Ian, the one that's the top voter right now, I'm going to throw to you first, and then I might have some thoughts on it too. But someone wrote, is there interest in DAC technologies that result in solid carbon that would be easier perhaps to store long term? So do you have thoughts on that, Ian?
Yeah, thanks. I think that's a really great question. So my take on that is, I think that there's definitely going to be a need for mineralization, which I think this is what storing solid in a or storing carbon in a solid form is really getting at. At the end of the day, I think if you can somehow interface that with a reactive capture scheme where you're using, transporting the carbon within a solution to your mineral. If that's thermodynamically possible for some minerals, that would be very attractive. And just bringing down the overall number of pieces of equipment that you need for any one DAC process is going to be key in lowering the overall price of CO2 that you're storing.
Okay, great. And I'll note that it's not a DAC technology per se, but our colleague Mark von Keitz is looking at this from the point of view of methane, a methane pyrolysis program converting to hydrogen and solid carbon. So again, not removal from air, but I think similar possibilities and very much focusing on what can you do with all that carbon. I think that's turquoise hydrogen. Maybe we were talking in the last session, we were saying that I think somebody called nuclear pink hydrogen, but that's another example. Question for me, what needs to change to make DAC economically feasible on a large scale? That's a really good question. I really focused on the energy input, which is significant, but a massive part of the cost of DAC is capital cost. So that is, the air contactor, that is the, whatever medium you're using to do that, and how stable is that medium and how low cost. If you have, hey, I've got this really great material that's fantastic at capturing CO2 from the air, and I have to replace it every 6 months, that's gonna be a very expensive solution. And so I think a lot of research is focusing on all parts of the system, on air contactors to reduce pressure drops and operational energy, but capital cost absolutely has to be part of that. And I think in general, I still think there's a lot of possibilities. I've mentioned a few different types of energy input, and I think a lot of early DAC was sort of very much in the same vein of point source CCS systems as far as thermal regeneration. So I think there's lots of possibilities, but it is both capital and operationally very energy intensive to do. So we need breakthroughs across that scale to really get there. Another question for Ian. So for field precursors, which carbon-containing molecules seem the most promising to aim for based on value per carbon captured and the cost of making valuable fuels, and why? So what do you think about that?
Yeah, definitely. Thank you. That's also another very good question. So what this is really going to come down to is energy efficiency of your conversion step. You're going to want to probably produce the most simple molecule that you possibly can. So that's going to go down to C1s like carbon monoxide, formic acid, and methanol, because you can produce them with very high efficiency. If you take a look at a lot of CO2 electrolysis, it's not necessarily the bicarbonate electrolysis, as that's kind of an up and coming topic, but producing things at 70%, 80% efficiency is going to be key, because you're paying a lot for this cheap electricity. It sounds like it's cheap electricity, but on an energy per dollar basis, it's quite expensive compared to a fossil fuel that you're taking out of the ground. So simplicity is going to be key.
Okay, thanks. Marina, there's a question for you. Where do soil carbon emissions and sequestration in the realms of farming fit into CO2 removal?
Yeah, so that really highlights one of the key importances to having biogenic feedstocks under consideration as carbon negative building materials. It makes a really good sink for those types of sources that would otherwise result over time in emissions. If you think about agricultural waste and residues, things like straw. And so even if those types of storage mechanisms are more temporary than the longer term ones, if you look at the timescales, including in the chart I showed from Lawrence Livermore, it buys us quite a bit of time to then convert to more permanent storage solutions. But it's an immediate way to get rid of what would otherwise result in longer term emissions if they were, otherwise just left as is in terms of agricultural waste. Okay.
Thanks, Marina. The current top vote getter for questions is, do you think CCS is important? How does it compare to other directions? As the guy running a CCS program at ARPA-E, I'd say, of course it's important, but it's one of those technologies that can help us reduce emissions, and there are multiple ways of doing that. And I think at ARPA-E, just reducing emissions is such a big part of what we do, whether it's nuclear or renewables or energy storage. So there's a program called Flex, which is focusing on point source CCS, which is not direct air capture, but how that might look on a grid with lots of renewables. We think it really could be valuable, but we think it's not going to look quite the way people thought when they first conceived of CCS. It's going to have to be more, more flexible and look different. And that's something that the Flex program is looking at right now. So we do think it's important, and that's something that we're working on. Jack, question for you. Is there target energy conversion efficiency for the energy generation and storage systems, some of the examples that you noted in your fast pitch? And Jack, you're muted as well.
Sorry, yeah, thanks. It's a really interesting question. The traditional paradigm has been to look at efficiency as kind of as a proxy for overall cost. What I'd like to suggest is maybe we look at some new rules where we don't necessarily consider efficiency as much as we consider cost and impact. If you look at, for example, underground wells and mines where you have this tremendous hydrocarbon resource base that's basically completely unutilized, efficiency is really less important than the impact and the net delivered energy cost. So I'd like to maybe try and shift the conversation away from efficiency. And also, I would say, if you look at the complexity of the equipment to achieve high efficiency, it gets to be very complex, as opposed to looking at very simple devices, which may be more easily deployed, more easily maintained, and again, driving down that delivered energy cost.
Yeah, that's a really good point, Jack. And I think there's some observations we made. I was just mentioning Flex. I think capital cost and simplicity, and just reducing that as much as possible. Depending on the operational profile, there could be more benefits to doing that than to try to eke out every little point of efficiency. So that's a really good point. Someone asked me, Scott, you talked about DAC as a demand response resource. How big could that be? What function would it serve on the grid? That's a good question. It's not clear. So first question is, how big does DAC become? And that depends, I think, on a lot of other approaches, particularly on biomass. Like the more that we can use biomass resources, that probably means less need for DAC, which is actually, probably better overall. But that's a question. There's a scalability one we'll get to later that I think that's related to that. The way that I did the calculations, I think it was the electricity consumption was a few percent of the overall U.S. energy. So it's a few percent. And so if you think about all the natural disasters that have been happening, whether it's wildfires or hurricanes or very cold winters, it's not going to solve that by itself. But the ability to turn off a few percent of your load could really help stabilize parts of the system. And again, this is in addition to work ARPA-E is doing on transmission and distribution and system flexibility. So it's not going to solve the problem by itself, but it's a resource that could help. So that's a little bit high level of an answer, but I think it's something interesting to look at. Marina, do you have any interest in chemicals made from fermenting sugars that could be used as building materials?
Yeah, that's an interesting question. I mean, in general, what we're looking to do here is, and pose the question is, can we store more carbon that's emitted in the full processing? So if you have a way that does that, then sure.
Okay, great. And I guess, Marina, in general, I should also note, you hosted a workshop, a few months ago on this topic. I guess, based on some of the things that you've been talking about here and sort of the inputs that you got from the workshop, are there sort of, some particularly high-level insights that you want to share that they're sort of the key things you learned as a result of that workshop?
Yeah, thanks, Scott. Highlight this also earlier. Thinking about ways in which we can complement recycling and ways in which we can design for disassembly and for ultimate end of life, so that the outcome is not just the status quo of landfilling, are really critical. And how can we kind of go beyond that to really consider ways in which scaling these types of solutions in a cost-effective way by providing some type of additional performance advantage into the built environment. That's a real challenge because cost is, it's all about cost in the construction industry, and it's very difficult to unlock a quite kind of risk-adverse industry in that sense.
Okay, Yeah, and like I said, I think there's some information from that workshop online. There's a lot of really good content there. So thanks, Marina. Ian, question for you. What is the technology readiness level of CO2 to formic acid?
Yeah, definitely. Thank you. So actually, that's already a commercial system from dioxide materials. They have a CO2 electrolyzer that produces formic acid. That is one of our performers. There are probably a couple of other companies, but that's the one that comes to mind off the top of my head.
Okay, thanks. Current top voter question for DAC, scalability is also key. How does engineered capture solutions compare with nature-based ones? And where is the innovation on nature-based capturing methods? So great question. And there are some papers that talk about this. And I think people see DAC as essentially infinitely scalable as far as footprint, and there's a very large storage resource underground. So it just becomes sort of how much are you spending on capital for those sites and how much energy is required for other nature-based solutions. For biomass, for example, there are some papers out there, and whoever asked me this, try to contact me afterwards. I can send you some links. There are people that are looking essentially at how sustainable and scalable are nature-based CO2 removal. So biomass availability and transport and things like that. There's been a lot of really good reports, and I think there's again uncertainty in what that number is. There are some high scenarios, there are some low scenarios. There definitely are concerns about land use and water and food, and so it's complex, but there are people very much looking at that. And so I think the more that we can push on that in a sustainable way, that will lead to a lower cost system. But these there are engineered solutions that are highly scalable, but it's going to be more costly. And in future, in general, the way that we set up the Flex program, we assume that the future price of CO2 was set by the most expensive thing that you can do, which is DAC. So that's sort of, I think, the cap, if you will. But there's a lot of possibilities to what that look like. So that's a really good question. Jack, what is the total energy resource available in underground mines and wells? Let's just say, for example, in exajoules, if you have an estimate in hand.
I don't have a good number in hand, but just to give you an idea, I think we have about 300 years of coal reserves. That we're not talking about abandoned coal mines, just absolute coal reserves. Oil and gas, it's a little bit of an accounting issue. What you get to count is reserves, but we generally look at something on the order of magnitude 20 years of reserves that are put on the books, and then there's other kinds of reserves that are proven but not put on the books exactly, and those extend out to 100 years. So I think you could argue that we probably have order of magnitude maybe another 400 to 500 years of fossil reserves in the United States that are underground. Not advocating that we're going to tap all those, but again, the resource base is quite large.
Sure. Yeah, a long way from the peak oil days, right? Something very different. Okay, Ian, I'm going to throw this one to you. After capturing CO2, whether that's DAC or point sources or whatever, is ARPA-E or DOE looking at ways to transport it to some way of being utilized?
Yeah, so I think probably the easiest way to utilize CO2 is hopefully going to prevent the transportation of CO2. There are thoughts that we're going to have CO2 pipelines. They already exist, I think. And if the easiest method is probably going to be avoiding the cost of compression and purification and everything that you have to do, so that you can just utilize it directly on site to produce your useful product, which is, if it's going to be a point source, you then have a distributed product all around the country that's decentralized rather than hopefully transporting it to one central location.
Okay. Yeah, and like for example, enhanced oil recovery. I mean, that's a commercial process now. I mean, there are certainly pipelines to do it. And actually, you mentioned compression. I mean, whether it's DAC or point source, it's not as much as the capture part of the process, but compression is a non-negligible energy expense. It's usually to 150 bar. So that's another aspect as well. Marina, in your analysis, did you look at integrating something like CCS or DAC, like membranes or modular sorbent systems with buildings? I guess that's sort of distributed either CCS or DAC, if you will, to create carbon utilization pathways that are more, essentially more urban.
Yeah, so that would be a slightly different concept, if I understand the question correctly, where the building is already in place. You know, the economics would have to be in consideration there, but also where the carbon would be stored within the structure. You know, in a more active type building material that is continually absorbing carbon. But you know, we also have to take into account that the geographic diversity of the problem as a whole, and so a system like that would, first of all, only work in an urban environment, and second, you know, have to also consider the difference between a new construction where you could possibly incorporate a system like this versus an existing building in a retrofit where it may be extremely cost prohibitive to kind of add a complex absorption system like that after the fact.
Yeah, and I think there's a tie into the question below, which is asking about sort of like, you know, the main reason for high energy cost of DAC. You know, a small DAC system coupled with car exhaust might not take too much energy. Kind of, I guess maybe more of a modular approach. And there people definitely thinking about that. There are challenges, I think, with economies of scale in doing that. So you're integrating, you know, something to a car or a building that was never meant to do that. And you know, when people talk about that, they're like, oh, well, you can capture, you know, air from anywhere, and in principle that's true, but there are cost benefits in being close to good CO2 storage sites to reduce those transport costs, and also, you know, integration with, you know, where's, you know, like, you know, maybe if there's heat available in a car, that's possible, but you're adding a lot of complexity to the system. So I think there are rooms for creative approaches to what that looks like. Again, to point back to Flex, the point source CCS and direct air capture, you know, there's a lot of heat and electricity at power plants. You know, could there be integrations between that and DAC system? You know, that's something that, you know, is an idea, but we're actually trying to quantify that.
Yeah, and similarly, Scott, you know, when we think about these different feedstock mechanisms for building materials, that geographic diversity and considerations come in the urban versus the rural. So there are sources that we have at hand, whether it be timber or other approaches that make a lot of sense in certain parts of the country because they are geographically close, whereas in others, when you think about transportation and logistics, in other words, there's no one solution. It really has to be kind of a portfolio approach to all of these carbon utilization approaches.
Okay. This question is for Jack. Jack, you so overwhelmed our audience with great ideas that somebody asked, why isn't someone doing this already? So why are we not doing this already?
Yeah, that is always a great question. If it's such a great idea, how come it hasn't already been done? And I will say that, you know, every one of the technologies that I mentioned are known. For example, these thermoelectric generators are what we use to generate electricity on spaceships, for example, when they get out beyond where solar energy is possible. The biological approaches have been commercialized for wastewater treatment plants with electrolysis. The Dutch and the Germans are looking at the last two examples that I showed. But I think it really comes to a couple of questions. One is, like I said before, there's a whole paradigm of focusing on energy-dense fuels, which can be moved and then utilized at high efficiency. And this is really kind of a distributed energy play. So it takes a whole different mindset, you know, to focus on a distributed energy play. And then, of course, there are a lot of regulatory issues. So, for example, just the simple fact that you've got a coal mine or a well, there are rights to those, you know, those assets, those underground assets. And it's not necessarily clear if you wanted to repurpose a well, how do you properly compensate the people who own the underground rights, the mineral rights? What mineral rights do you ascribe to a underground electrolysis as opposed to the royalties that you collect from oil and gas that flows to the surface? So there's a number of barriers here, both technical and commercial. And that's why I think, you know, you really need a whole new community to look at these opportunities and figure out what do you need to do technically, economically, and even, you know, legally, if you will.
Okay, well, we've got about 1 minute left, so we've got time for one or two quick questions we'll try to get to. Ian, Is bicarbonate electrolysis the only technology that can be paired with DAC in a reactive carbon capture approach?
No, if you're going to use, a solid sorbent and you use, amines, you could also do something like hydrogenation of the carbamates that are formed from the amine capture. There's also, plasma regeneration of some sort of sorbent. It's kind of in the early stages of development, and I'd love to hear other ideas too.
Okay. Marina, this last one probably takes more time than we have, but it's a really good question. How do carbon storage concepts fit in with recycling strategies to reduce embodied emissions in buildings?
Yeah, so there was a panel right before this one that talked about the circular economy, and I'll start off by saying recycling itself can do a tremendous part in reducing those upfront emissions in buildings. Unfortunately, the way a lot of materials are designed today for building materials is not conducive to recycling. So we certainly need to take recycling seriously and develop innovations in that space. And I think that the ability then to also to store carbon is a great complementary approach to then further suck down more carbon to get to really these negative emission technologies that we've been talking about today. So if we can do both in a complementary fashion, it'll go a long way.
Okay, great, thank you. And with that, we're out of time. I know there were more questions that we had time to get to. We're sorry about that, but please do follow up with us afterwards. These are topics that we're really interested in. We want to talk to you. We want to hear more about you. So please do engage with us both at this meeting and afterwards. And so thank you for listening. Thank you for all the questions, and for my colleagues, thank you very much for giving me cool ideas.
Thank you.
Thank you.